So till now we have actually looked into a system in the state space form and tried to analyze the behavior of the system. Um, Firstly, we have studied it without the control action. So the homogeneous system or the unforced system, we have looked into it. We have discovered the properties of the system based on basically the properties of the state matrix A. So we have understood what is the idea of the eigenvectors, eigenvalues, what would cause the stability of the system, what are equilibrium points. All this we have discovered about the system. All these ideas about the system we have come to know. Then we actually studied the system properties with respect to the control action also, and we try to understand the concepts of controllability, observability, reachability, etc., and which deals with the system when we have the control action there. So controllability directly deals with the system when we are actually giving the control action there, and we are trying to figure out whether we are able to bring the system to a particular state, which is controllability, or bring or take the system to any state in future, which is reachability. And also we studied the conditions which would actually help us to understand the like structural conditions, which is dependent very much on the A, B, C matrices. So we those conditions about the rank of the controllability matrix and observability matrix we have studied, which actually gives us an idea about the controllability and observability. So till now actually all these things has been studied. All these are basically we are studying the system. So it is basically the analysis. We are analyzing the system. We are analyzing the We are noting down its various features, etc., etc., but we are really not doing uh, anything manipulative to the system, or what should I say? I should say in this manner that we are not externally trying to influence the system. We are not trying to influence the system externally. We have understood what will happen if the system is left in unforced condition. We have also understood what can happen if we actually give a controller, uh, if we actually give a control input, what can happen, whether the system is reachable or controllable, whether we can observe the states by looking at the output. So all these things we have analyzed. All these things come out from the structure, the state space representation of the system. However, till now we have not actually gone ahead and tried to manipulate the behavior of the system, and that is what we are going to take up this particular uh, lecture. So we are trying to go and manipulate the behavior of the system, and when such a question of manipulation comes in, we are basically talking about supplying an external control in the system so that get some desired behavior from the system. The idea of a desired behavior is very important. You cannot just keep on giving any input. So you need to have some intention in mind, what you are trying to achieve. You are giving this input. So with that intention, if a properly designed control input is given, then your intention will be achieved, and whatever you want the system to behave as, whatever output you want or whatever performance you want from the system, that you will get from it. That is the basic aim of the control engineer. That is the aim of the control engineer. although all the analysis that we have done so far is very important, otherwise this aim cannot be actually fulfilled. We have to do those analysis, but after doing this analysis, when we understand the system properties, we can now go ahead a step further and design the control input in order to manipulate the system in a certain way so that it behaves the desired manner, it performs in the desired manner. So, first we need to understand what are those desired behaviors which we are looking for. So, let us look at these problems. These are called the control problems, and there are three control problems which you will see in any system. We are trying to actually target these three control problems. So, control problem, these are control problems. Either you are trying to stabilize the system, or you are trying to regulate the system, or you are trying to track some or you make the system track something. These are the three control problems the control engineer is interested in, and these three control problems are distinct from each other, they are different from each other. So, we need to understand what exactly these are in order to understand what exactly we need to do. And when we understand these three problems, we would actually discover that though these three problems are different, they are actually the same problem. So, we would actually try to solve this same problem. Actually, what is the underlying commonality between these three problems? We will try to solve that, and that would make all these three problems get solved at the same time. So, any problem you give, you can solve it using the same method. Let us understand what we mean by stabilization of a system. So, in stabilization, so let us assume a state space. So, for our purpose, we assume a second order state space, but it can be any nth order. So, why there is a lag in writing. So, anyway, this is the state space, and if you think about the states evolution with time, so we have a time graph and a states and a trajectory graph. So, this whatever is in this particular graph will be the trajectory, whatever is in this particular graph is the state evolution with time. So, basically here we are talking about two states, but we can have any number of states. Okay. So, what is the stabilization problem? The stabilization problem is basically the problem to come to the equilibrium point, that is stabilization. Stable, the system is stable, that means the system is no more moving, the system is at rest, then the system is termed as stable. That means no matter where you are starting, you must come to the origin. You may come at with any trajectory, this is not so important in the problem of stabilization. So, you can start from here, suppose this is my initial point, you can come in this way, you can come in this way. So, all these are valid, you can come in this way. So, 1, 2, 3, any trajectory you can take, it does not matter to us as long as we are ultimately coming to the origin and then staying there for all future times. That is the stabilization problem. Stabilization problem means that your xt tends to 0 as t tends to infinity. This is has a particular name called asymptotic stability. At least we are trying to have asymptotic stability. The stabilization. In this particular graph, what you will see that your states, I am drawing only one state. So, there are two states, but drawing only one. It will have a evolution like this. It can also have a like this. It can have a evolution like this. So, any of these, suppose 1, 2. So, this is the problem of stabilization. So, this is the problem of stabilization. Now, what is the problem of regulation? So, in regulation problem, we are actually having some point where we want to go. This is the x t desired position in the state space. You can start from the 0 position, you can start from any position basically. Start from any position, you are trying to go to this position. This is your x initial I. xi to xd you want to go. How you are going? This through this route, you can go to any route. As long as you ultimately go to D and then remain there fixed, then it is fine with you. Then it is fine with you. So, here you will have a xd point and I can start from anywhere, I can also start from 0. So, let us start from some point other than 0 here. So, I can come here like this, I can come here like this, I can come here like this, all these are values. This is the problem of regulation. Here xt tends to xd as d tends to. What is the problem of tracking? Simply remove the axis here. The problem of tracking, there is actually a desired trajectory in this case. So, first stabilization, there a particular place has to be reached, which is the equilibrium point. The equilibrium point has to be reached in stabilization. In regulation, any point can be reached, but even other than the equilibrium point, but that point must be constant. So, you have a particular destination to reach. Now, what you are doing? You are trying to take a trajectory here. So, suppose I have some initial, well, let us assume this 0 for this example. Suppose I want to cover my state space like this, and this is the final position. I want to go in this route, I want to take. So, my x1, you see x1 is taking so many values with time, x2 is also taking so many values with time. So, x1 is going in this direction and x2 is going in this direction. So, when you actually draw it, so this is exactly the trajectory that I wish to take basically. This is exactly the trajectory I wish to take. However, I may have started from somewhere other than the origin also. Suppose I start from this point then what is my desire is that I track the trajectory as soon as possible and go like this. So, you can have some controller which follows this particular blue trajectory, which I indicate with 1. You can have another controller which will follow like this, number 2. So, all these different actual trajectories will depend on the actual controller you are using. The desired trajectory is the red one. Okay. Now, it may so happen that if you start from the 0, which is the starting point, even then you might not follow this trajectory exactly. You might be deviating a bit and then start to follow, might so happen. It all depends on your controller. Okay. In this graph, what you will have for a particular state, you will have uh, a desired evolution. You will have a desired evolution. Suppose this is the desired evolution. Here this one some x1 for the x1 I am trying to draw xf1 suppose. So, this is my desired evolution, but what I may see that some control input will make it like this, okay, and then it will track. Some control input can make it like this and then it will track, and if the third one which I started from origin, it may also have some deviation, then it can start track. But here the idea is tracking. That means xt must tend to some x b e. So, it is not a constant anymore, it is a desired trajectory. So, you know all the points in time of this trajectory. You know the time also, you know at you should reach this particular point at this particular time, that also you know. The entire trajectory is known and that you want to actually follow. Your actual, this is your actual, you are trying to follow this and you want to do that as quickly as possible, but we write it like as t tends to infinity. That means with time I will reach the trajectory and then I will stick to it. Yeah. Obviously, you can understand as fast as we can reach the better for us, but the definition wise we actually define asymptotic convergence. All these are definitions of asymptotic convergence. The first one is asymptotic convergence to 0, second one is asymptotic convergence to a particular destination point, third one is asymptotic convergence to a particular trajectory. All these are asymptotic convergence. Okay. So, what is common to all this thing is the asymptotic convergence. Basically, common to all these stabilization, regulation, etc., tracking, the common thing behind all these things is the asymptotic convergence. And you can basically, you have a state space representation like this, then in the first problem you are trying to make x tend to 0. If you have a regulation problem, this is stabilization. If you have a regulation problem, then you are basically, you can basically construct a new variable, new error variable E, as x minus xd, and then your intention will be to make error go to 0, right. Your intention will be to make error go to 0. In the third case, you can have this is xt minus xd, this is xt minus xd t. In the third case, you can have a error variable defined like this, and then your intention again is to make error go to 0. The first case, you can assume that xd is 0. If you assume xd is 0, then the first case is also an error going to 0, but the error here is the state variable itself. So, in all these cases, basically we are trying to stabilize a system. In stabilization, regulation as well as tracking, in all these three we are basically trying to stabilize a system. The first case, it is the system itself. In the second and third case, we are trying to stabilize the error system. So, it is as good as to study stabilization only. If we study stabilization, then we are automatically studying regulation and tracking, and we would be able to deal with those two problems also. Only we have to remember that we need to construct a error variable and go to the error state space. Yes, we need to come to the error state space, and error state space we need to come to, and then we have to stabilize the error state space. Let us see the error state space. What is the error state space? Is it very unfamiliar to what we are dealing with right now? So, for the regulation problem, xt minus xd is the error. What is E dot? E dot is x dot minus xd dot. Do we need to write xd dot? No, because xd is constant, it is x dot. E dot is basically ax plus b, but what is x? X is e plus x. So, we know that this side is e variable. So, this side we also should have e variable. So, this is basically coming out as ae plus axd plus, right. So, this u, so instead of bu, you are getting axd plus bu now basically. So, in this control action, you can take care of your this axd, or I can say in this way, you since you know this what is axd, you can always subtract this out from the right hand side by supplying a appropriate control. So, basically it is same as your AE and a B coming here. So, it is same as this particular form. The form of equation is, in this case again, if you do E dot, you will have x dot minus xd dot. Here you will have xd dot, but that is equals to ax plus bu minus xd dot. X is what? X is ae plus axd, ae plus bu plus axd minus xd. These two you know. So, I should not say subtract, basically you can add actually. So, here this thing, so this is what control input you are supplying. I should draw the block diagram that would explain things better. What is the block diagram here? So you have the plant. Suppose I am talking about the E plant. Suppose I am talking about the error plant. Okay. So in the error plant, you are having this integrator 1 by s, whatever is coming out. So this is your E dot. From here you are taking it as A, your E, taking it as A, and then you are coming here. So this is E dot. What is E dot? E dot is AE plus something, which is your BU, right? So your U you are forming using your E. Suppose there is a controller. So this is our what we will design controller. With this I am getting a U, and this U you are passing through a B, adding it to this, and you are getting this. This is a normal situation. So if you don't have the error, suppose you replace E by X, then this state space equation I have drawn in the block diagram above. In case I am getting this error thing, then basically the error system, in the error system I have to add a AXD for the regulation problem. So I have to add here. So I can also add a XD here basically, and then supply and add an XD here and then supply it to A. Then for the tracking problem, since I know what is my XDT and XDT dot, this I would know because I know the trajectory. I can supply the XDT here and XDT dot here. That would be my block diagram. So I would be able to actually provide these additional inputs. These are coming as additional inputs which I know. I don't have to design these inputs. I already know this, what additionally is to be supplied to the error system, and I have to design this U only. This U I need to design. So then the problem is basically I can come back to this problem. I can come back to this problem and solve this particular problem. So for stabilization, okay. Because these additional inputs which I am giving to the system, these additional inputs which come to the system like this, if I now subtract these inputs from this system, then what remains is basically this particular system. So the stabilization of the x dot equals to ax plus bu system is what we are interested to study. That will be sufficient for even regulation and track. So with that idea, we would actually go ahead, and here we introduce the basic controller, which is state feedback controller, for our purpose, for our design purpose. Introduce the state feedback controller. So what is the state feedback controller? The state feedback controller is basically this. Basically this u equals to minus k. Simply a linear relationship with the states. So when you So that is why it is called state feedback. So it needs the information of the states, and the states are fed back so to the system. So originally the system was this much only, x dot equals to ax, this is the system, but you are feeding back the control input with like this. So you are feeding back, you are taking the states, and then you are creating the control action as u equals to minus kx, and then you are feeding it back to the system. So that's why it is called state feedback controller. So when you apply this control action, basically what your closed loop system equation will be is this. Closed loop system equation becomes this. So it is, again you see, it is becoming the closed loop system as if becomes an unforced homogeneous system that we already studied, where the state matrix is no longer A, but it is A minus B. So the solution would be e to the power of A minus bk x0, and we know that what we need for stability. So we are looking for stability, right? Xt tends to 0. We are trying to do that. So for stability, the eigenvalues of the closed loop system matrix A minus bk needs to be in the left half of the plane. So if you could place them in the left half of the plane using the gain k, this k is in our hand to be designed. This k is what we need to design. So if we can design a k in such a way that the eigenvalues of the closed loop matrix A minus bk goes to the left half of the S plane, then our job is done. Then xt will tend to 0 as time tends. So the question is now, are we will we be able to design a k like that, that is taking all my eigenvalues of A minus bk closed loop matrix the left half? The answer is that yes, it can be done, but if and only if a double if is if and only if the AB pair is completely state controllable. This is the condition. That means if AB is completely state controllable, you can actually design a K matrix which is going to bring us closed loop system eigenvalues. But this statement is not sufficient, because we need to actually know what that K would be. And while knowing what that K would be, we would actually also prove that AB needs to be state controllable. Let us go ahead into looking into the proof. So we would be dealing the system in the controller canonical form. The state feedback controller we will design in the controller canonical form. So we would be coming to the controller canonical form using a state transformation, using a transformation similarity transformation, and we would assume that that we have a gain, we have a state feedback gain Kc equals to Kp in the controller canonical. The controller canonical form gain Kc is related to the original system gain K with this relationship, where P is the similarity transformation. So if we assume this, then we can see that if I write AC minus BC Kc, we write AC minus BC Kc, which is the this is the closed loop matrix of the controller canonical form when we supply this Kc state feedback control action. Then if you expand, this becomes like this, and then if you evaluate the characteristic polynomial of this matrix of this closed loop system, you see that the characteristic polynomial is same as the characteristic polynomial of the closed loop system of the actual system representation, which is not necessarily in the controller canonical. We have started with some representation ABC. There, if you apply the gain K, you would get some closed loop closed loop system which has a matrix A minus Bk. So it will give rise to a characteristic polynomial. Now I see that if I choose Kc equals to Kp, the controller canonical form, and apply the state feedback gain as minus Kcx minus Kc x hat here, because we have changed the coordinate x hat, then the characteristic polynomial of the controller canonical form, closed loop controller canonical form, will also be same as the actual characteristic polynomial of the actual system. So that means this is a valid, this Kc equals to Kp is a valid assumption. It does not change the eigenvalue placement, does not change the eigenvalue placement of the closed loop system when we are supplying the control action, control input. So noting that the controller canonical form is of this form, AC and BC are in this peculiar manner, this is the peculiarity of the controller canonical form. This is almost like the phase variable form, right? But BC is here 0 0 dot 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 1. Okay. So noting that the controller canonical form is like this. So here let us see what happens when we supply the state feedback controller Kc. Suppose I take my Kc as like this. This is a vector. Kc is a vector, assuming that my control input is a scalar control input. We are trying to make a scalar control input. So this Kc is like this. So when I supply this Kc, then AC minus BC Kc becomes like this. And you see only what happened basically, these an minus 1, these coefficients in the last row of the A matrix, they simply get changed by including the kn minus 1, these gains. They simply include or append the gain ki's into themselves and nothing else changes. So the controller canonical form keeps the same matrix, state matrix structure unchanged even after state feedback control is applied. That is the peculiarity of the controller. Controller canonical form is such a form where even after state feedback controller is applied, the state matrix structure remains unchanged. State matrix structure form remains unchanged. That is the controller canonical. What happens? What is the utility of this? The utility is very straightforward. If I ask the question, what is the closed loop characteristic polynomial? Can you tell me? You will say yes. It is very obvious now, because I know that the coefficient of the characteristic polynomials are these last row elements, the controller canonical form. So since the form does not change the closed loop coefficients, closed loop characteristic polynomial coefficients are these. So the characteristic polynomial of the closed loop state matrix AC minus BC Kc are this, and if we desire the eigenvalues to be placed at some particular location, then we can actually form a desired characteristic polynomial always. So these lambda 1 to lambda n, let them be the desired location of the eigenvalues, then I can always have the desired characteristic polynomial. I simply need to expand this and I will get the desired characteristic polynomial. Suppose there the coefficients are C1 to Cn. Then if I wish that with my gain Kc applied to the controller canonical form, I would get the desired characteristic polynomial same as I would get the closed loop characteristic polynomial, same as the desired characteristic polynomial. Then what do I need to do? I simply need to match the coefficients. I simply need to match A1 plus K1 with C1, A2 plus K2 with C2, etc., etc. And in that matching, I can get what my Ki for all the i's. K1 would be C1 minus A1, K2 would be C2 minus A2, likewise. So now when I have got all my Ki's, I can now calculate back the state feedback control gain K of the original state space representation using this. So nice, so easy, right? So easy. But one thing we have not done. What is this similarity transfer? This we need to know. Otherwise, we will not be able to do the calculation. So let us put this as a fact. You can take it for third order system or fourth order system, probably you will be able to do it. You can check it, that the inverse of the controllability matrix of the controller canonical form, inverse of the controllability matrix of the controller canonical form would be of this form, would be this. So this is the form of the inverse of the controllability matrix of the controller canonical. And of course this is full rank. Of course this will be full rank, as you can see from the structure, and hence the you can always calculate the similarity transformation P if you know the controllability matrix of the original system. You can calculate the similarity transformation P. Now also to note that since you are talking about a similarity transformation that has to be non-singular, and your inverse of the controllability matrix of the controller canonical form obviously is non-singular, your controllability matrix of the original state space representation must also be non-singular. That means of full rank, must be of full. This means the original state space representation must be controllable. The AB pair there must be controllable. That is how we prove the controllability also, that controllability is required. We also come to understand how we can actually find out the gain K of the control action, state feedback gain. There are two other methods of finding the gain K. One method of that what we saw by going to the controller canonical form, but that requires calculating P. There is also a P and P inverse. There is also some direct method which you can follow. The direct method, direct substitution by K you assume something and then you evaluate the characteristic polynomial and compare with a desired characteristic polynomial. You can straight away do that. You don't have to go to the controller canonical form actually. You can straight away do this for any state space representation given. However, this method becomes tedious for system or order 4 and above, because you have to calculate the characteristic polynomial of this A minus BK matrix, which is not very straightforward. In controller canonical form it is straightforward, but otherwise it is not straightforward. So you have to do the calculation. So it becomes tedious for system order 4 and above. The other is Ackerman's formula. So here you can simply remember this formula. There is a derivation which is long, so I will not go through that. You can simply remember this formula. This is 00001 So this is the length of n, okay, n being the system order. So all n minus 1 zeros and then a 1. Then what is C inverse? C is the controllability matrix of the given representation, inverse of that. What is phi A? Phi S is the desired characteristic polynomial. You always have to go to the desired characteristic polynomial. You have to find that in any case, in any of these methods, you have to always find that. Desired, you know where you want to place the poles. Exact location of the poles you can actually give. So you will obviously give some locations in left half plane. So some location, whatever you choose or whatever is given by the given in the problem to you, you can find out the desired characteristic polynomial always. So you find out the desired characteristic polynomial, but in place of S, you replace with A, which is the state matrix of the original system, the open loop state matrix. You replace phi S with the S of the characteristic polynomial with A, and you get phi A. And then if you calculate this, you will get the gain. This is Ackerman's. Remember one thing, that all these formulas that we have said are or these are for like scalar control. Okay, if you have multiple control input, then this will not be a single row. This k will not be a single row. This will be two rows there. Okay, keep that in mind. You can do that with direct substitution using multi-input also. Ackerman's formula you cannot do with multiple input. There is some other way of doing it which is a bit involved, or there may be Ackerman's formula for multi-input. I have to check. I have not checked that. But when you are designing in MATLAB, they have a beautiful command called place command, which can deal with multiple input. But when you are doing in hand, you have to do direct. You are given multiple input. Normally, single input is what is for pen and paper. But just keep this in mind, because in MATLAB you deal with multiple input control. With that, I end the lecture. Thank you for